So we're asked to draw the root locus diagram for the system shown, and I'm going to follow through the steps that I did in the recap video for drawing root locus diagrams. So the first step is to figure out what our open transfer function is, so that we can identify the open loop poles and zeros. Alright, so our open transfer function is when we're not considering any feedback. So it's just going to be these two blocks multiplied together, which is k on s plus 1, s plus 2, s plus 3. And looking at this, we can see on the top line that we have no zeros because there's no values of s on the top line that we can set to be a certain value that then forces everything on the top line to go to 0. So no zeros. But for poles, if we set s to be equal to -1, then that's going to be causing the whole bottom line to go to 0. If we set s to be equal to -2, same thing happens here. And if we set s to be -3, same things happen here. So that's our 3 open poles that we have. And now we can go ahead and draw them onto our root locus diagram. So coming over here, setting up my imaginary and real axes. So I have 3 poles, and they're at -3, -2, and -1, no zeros. Alright, so the next thing that I can look at is doing my real axis line segments. So for this, I'm going to look at my diagram, and I'm going to move from right to left, and I'm going to join together every second pair. So moving this way, the first one I encounter is this pole, and I need to join it to the next one. So there's going to be root locus on the real axis in here. And make it look a bit neater. There we go. And then there's not going to be nothing in here, and then I need to join this one to the next one. And at the moment there isn't actually anything there, but I'm still going to draw it in. Okay, it's supposed to join to the next one. And what we're going to find is that because every pole needs to be joined to a 0, we're going to end up with an infinite 0 all the way out here at -infinity on the real axis. But we'll get there in time. Alright, so the next thing that we need to think about is these infinite poles and zeros. So at the moment, we can see that the number of finite zeros is 0 because we didn't have any. And the number of finite poles is 3. So as a result, we need to have 3 infinite zeros so that the number of poles and zeros are balanced. Okay, because if we add 3 to here, then we'll have 3 equals 3. And because we have no zeros, every single pole on our diagram is going to need to join to an infinite 0. Oop. Cool. Alright, so we'll come back to that in a moment. So the next thing that we need to look at is our asymptotes. And we have 2 equations that we need to apply. The first one is for where it touches the real axis. So the equation is this. Alright, so this is the sum of the finite poles. So we have poles at -1, -2, and -3, so that's the total added together. And we have no zeros, so that goes away. We need to divide by the number of finite poles, which is 3, minus the number of finite zeros, which is 0. So putting this into a calculator, we find that our value is -2. So next we need the angles. Again, we have an equation. Alright, so we need to pick a couple of different values of k to perform this equation. So let's start with k is equal to 0. So if we do that, 2 times 0 is 0, and we've got a 1 here, so we get 1 times 180 on the top line, and the difference between the number of poles and zeros is equal to 3. So we end up with an angle of 60 degrees. So let's increase k by 1. So again, substituting k is 1 in here, we're going to get 2 times 1 plus 1 times 180 over 3 times 0, and this ends up being 180 degrees. So let's add one more and go with k is equal to 2. So again, when we evaluate this number, we end up with 300 degrees. So this time we're going to only have 3 angles that we need to calculate. That's because we need 3 infinite zeros, but if you're unsure, you can always do the next one. So if you do k is equal to 3, and what you should find is that you end up with a repeat of 60 degrees. So you'll end up with an answer that's 360 plus 60, which is the same as, you've just gone all the way around the circle and a little bit more again. So now we're up to the next step, which is looking at the breakaway points. Break-in points. So applying the equation to calculate these points. Alright, so Zi is the zeros, and since we didn't have any, can get rid of that, and it's just going to go to 0, nothing to sum. And for the poles, we had 3 of them. We had at up here, -1, -2, and -3. So when we sub in, it's going to be sigma take -1, which is the same as +1. We're going to have sigma take -2, which is the same as +2, and sigma +3 as well. So this one isn't so bad to solve manually if you want to have a go at it. It ends up being a quadratic equation that you can solve using the quadratic formula. Alternatively, you can always throw it in your calculator, Wolfram Alpha, or even MATLAB to be able to solve it. So in this case, I've just put it in Wolfram Alpha. So this is just sticking it in, and we come out with 2 solutions here, which I'll just copy down. Alright, so only one of these is going to make sense. So if we go up here, what we know is that we have these 3 infinite zeros that are going to appear. So one of them is going to attach to this pole, and it's going to end up at negative infinity on that axis, since this is just going to keep going until it reaches it. So the other 2 are going to have to join to these 2 points, and in order for that to happen, we're going to need a breakout somewhere along this axis. So that's going to mean that our breakout point needs to be between -1 and -2. So if we look at what we calculated, we only have one point that is between -1 and -2. This is bigger than -2, so it's not going to be it. Okay, so this is the breakout point that we need to use. Alright, so let's go and put our asymptotes and breakout point on. So we know our asymptote is at -2. Alright, so that's this point here, and we said it was at angles of 60 degrees, so measuring from the positive real axis. Okay, so 60 degrees in here. It was at 300 degrees, which is going to be all the way around again, down to here somewhere. Okay, so all of this, that's 300 degrees. And the last one we had was at 180. So measuring from the positive axis, 180 is going to be backwards this way. So this asymptote is going to correspond to this root locus section here. And these 2 are going to correspond to what's happening in this center part. So we said that we have a breakout in there of negative 1.42, so let's say that's about here. So what it's going to mean is that we break out of the axis at this point. We know it needs to break out at up and down. So yeah, one goes up, one goes down. And with time, they're going to approach this straight line asymptote. So it should look something like this. Okay. So we can see here that it's definitely going to cross the imaginary axis at somewhere down here, and also it will cross somewhere up here as well if I extend my axis a little bit. Alright. So we have two imaginary axis crossing points that we will need to determine. Okay, so for this, what we need to do is look at a Ruth table, and we're going to try and solve for the case of marginal stability, which is where we force a row of zeros in that Ruth table. So remembering back to our stability stuff, we always want to do it on the closed loop transfer function. So that's going to mean that we need to solve for G closed, and we know that negative feedback always follows this pattern. So G open is our open transfer function, H is the feedback. So we already worked out G open before, it was this one here, and we can see that we have unity feedback, which means that our feedback function is equal to 1. So we can substitute both of those into our closed loop transfer function, and because we have unity feedback, what we're going to find is that our closed loop transfer function looks like our open one, which was this one here. Okay, that's our open loop transfer function. And then when we close the loop, we end up with the numerator also appearing as an addition on the bottom line when h is equal to 1. So you can go through and solve that properly if you're up for it. Otherwise, this is kind of a bit of a shortcut. So I'm going to need the powers of s expanded out in here. So if you expand out this bottom line, you end up with s cubed, 6s squared, 11s plus 6, and then you also have the k carried down as well. So let's go and set up our Ruth table. So we take our highest power of s, which is 3, s squared, s to the 1, s to the 0. Give ourselves a couple of columns. So filling out, the coefficient is 1, 6, 11, and then this is the constant 6 plus k, and everything else can be zeros as much as you need. So if we're going to look at forcing a row of zeros, let's start with filling in this cell here. I'm going to call it A. So we should be able to get it from looking at the negative of the determinant of this matrix here, divided by the pivot element, which is equal to 6. So if we expand this out, alright, so we're going to get negative of 1 here times 6 plus k minus these two multiplied together divided by 6. And if you clean this up a little bit, it comes to 60 minus k, and the bottom line is still minus 6. So we can fill this in. And what we were looking for to find the imaginary axis crossing is we need to force a row of zeros in this Ruth table. So we can do that on this line here, because we've already got 2 zeros. So we just need to ensure that this one is a 0 as well. And we need to find what value of k will cause that. So let's do this up here. So we need to figure out when this cell is going to be equal to 0. So if I multiply the 6 up, I'm just going to be left with 60 minus k, and therefore k is going to be equal to 60 for this cell to be equal to 0, and thus the entire row is of zeros. So what we need to do now is take this value and use it in the row above. And we need to write the row above as a polynomial. So because this is the s squared row, this is like our x squared. So we can say it's the coefficient for the s squared, I should say. So this becomes 6s squared. And this here is like our constant, because this was s cubed, this was s squared, this is s to the power of 1, this is s to the power of 0, which is our constant. So we can write this as 6 plus k. And we're going to set it to 0 as well. So now we need to look at what happens in this marginal stability case where we stick 60 in for k. So let's do that. So what we're going to be left with is, this is 66. We should be able to figure out what value of s this equation should be equal to. So if we move this to the other side, we're going to get negative 66. Divide by s. And then to get rid of the square, we need to square root. So this is the same as like square root 11, of negative 11, I should say. And as a result of squaring a negative number, we're going to end up with an imaginary number. And it's about 3.32i. So this here is our imaginary axis crossing. It's at 3.32i, plus or minus from the square root. So if we go back to our diagram, okay, we know that this point and this point where we cross the axis is now at 3.32, and it's the imaginary axis, so that's where the I ends up going. Okay, this is the positive one and this is the negative one. So we've now marked in all the points of interest that we can possibly do on this root locus diagram. So all that's left is, probably if you have access to MATLAB, is just to double check that what you drew looks similar to what MATLAB calculated. So if we go and have a look, I've written myself a little code here which will draw me the root locus diagram. Remember that for MATLAB you don't put the k in your transfer function. It does that for you when you apply this root locus command. And this is what it plots. So we can double check our imaginary axis crossing. So somewhere about here. So you can see that the real component is almost 0, and we have a value of 3.29i. That's pretty close to the 3.32i. So that's pretty good. Yeah, the inaccuracy is just because we're not exactly on our axis, imaginary axis. And the other point we can double check is probably this one here, where we break out of our real axis, and we've calculated the same thing as what we've got here of negative 1.42 for where that breakout point occurs. So that definitely validates what we have drawn for our root locus diagram. That's all there is. See you in another video.